Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. We were discussing in the previous module the Laplace equation and its use to find out electric field. We set up the problem of parallel plate conducting system. We will solve that system in this module first to show you how one can calculate electric field E and correspondingly the quantity capacitance of these two parallel plates using by solving the Laplace's equation. Now we see that Laplace's equation between the regions will have this form, right. So del square V is equal to 0. Why should it be equal to 0? Because I am going to assume that the medium in between is filled with a perfect insulator having a permittivity of epsilon. Okay, so it is a complete insulator in between these two plates. As I said, the plates themselves have an area A which is quite large compared to the thickness of the plate. So A is much larger than D. There is a reason why I consider A to be much larger than D, because all the calculations that we are going to do are very nice and very excellent calculations as long as you are in the center of these plates. Okay, when you come to the edges, the electric fields, you will see that one sooner in other modules, that these electric fields won't be normal to these conductors and they will actually bulge a little bit. Okay, so this bulging phenomenon is what is called as bulging of the electric fields is what is called as the fringing effect, and the fields that you are going to generate will be what is called as fringing fields. So we are going to neglect this fringing field because my goal is to try and show you how to solve this Laplace's equation and then maybe obtain the capacitance value for this system assuming the condition A to be much larger than D. Let us not complicate our life in the first example itself. So I have del square V equal to 0 in 2 dimensions. This is clearly the case of a 2 dimension. I can write this as del square V by del x square plus del square V by del y square equal to 0, with the x axis taken perpendicular to the plate. So this is how the x axis is going, and then you can consider this to be the y axis, and along this axis will be the length or the axis z, which we do not really need to worry about it at this particular point. You do not even need to worry about the second term, this del square V by del y square term, because the condition or if the symmetry of the problem is such that if you move around or if you move from the top plate to the bottom plate or from the bottom plate to the top plate, you are actually seeing or you are moving at a certain distance, right. Okay, and then so when you start from the bottom plate, as you keep moving and you hit a distance of x equal to d, which happens to be very quickly, right, then you see that there is a second plate. Okay, however, if you stand in the middle and then move sideways, so you stand here and then move along y, so we assume that this length of this one and hence the total area of the plate is so wide that you will have to move substantially in order to encounter the end, and because of that reason we can neglect any variations of the potential V with respect to the y axis. So as you keep moving along this sideways, okay, either onto the left or to the right, you encounter the fringing fields or you encounter the boundaries at a much larger distance compared to the fields that you the plates that you encounter when you move along the x axis. So the fields are strongly dependent on x and extremely weakly dependent on y, which allows me to completely neglect this del square V by del y square term. So the equation that I am trying to solve now becomes very simple. I have d square V by dx square equal to 0. How do I solve this? Integrate once. Integrating once gives you dv by dx equal to some constant c1. Integrating this one again gives you v of x equal to c1x plus c2. This is something that you know from your differential equation. So integrating this one, you get c1x plus c2, where c1 and c2 are to be determined. Okay, we do not know what these are and we need to determine. Do we have enough information to determine this constant c1 and c2? Yes, we do. We know that the potential everywhere on the bottom plate happens to be equal to 0, and the bottom plate is actually kept at x equal to 0, and potential everywhere on the top plate happens to be equal to V naught, and the top plate is kept at x equal to d. Okay, so I apply the condition that at x equal to 0, the potential that I am finding or the potential that I have must be equal to 0 everywhere, because this happens to be the bottom conductor which has been grounded. So go back to the equation V of x and substitute x equal to 0, which will give you 0, okay, that must be equal to C1 into 0 plus C2, right, C1 x plus C2 x equal to 0. Clearly C1 into 0 will make this entire thing go to 0, and the condition that you are going to get from this one is that C2 equal to 0. And the condition that I have applied is actually the boundary of the problem, right. So the bottom plate defines the boundary, and therefore this is called as boundary condition. So I applied a boundary condition 1 saying that at x equal to 0, potential V equal to 0, substituting into the expression that we have obtained allows me to find out C2 equal to 0. At x equal to d, potential is some applied potential V naught. So V at x equal to d is equal to V naught, the potential on the top conductor. This must be equal to C1 into d, right, x equal to d. There is no C2 here, C2 is already 0. So this allows me to write C1 as V naught divided by d. So my general expression for the potential V of x can now be rewritten as V0 by d. So V0 by d times x. Does it satisfy the two boundary conditions? The potential V of x that we have written, does it satisfy the potential the boundary conditions? Yes. At x equal to 0, this right hand side quantity V0 x by d is 0, and at x equal to d, this right hand side quantity is equal to V naught, which is what we have for the upper conductor or the top conductor. Okay. I have now found out V of x. There are two questions I need to answer. Is this potential, okay, unique? In other words, is there any other function of x which would satisfy the boundary conditions, okay, and satisfy Laplace's equation? Unfortunately, the answer is no. Okay. So you might, for example, think of this. I am just trying to pull a certain this one out from my side. So let us say V0 by d square into x square. Okay. So this field clearly will satisfy the boundary condition. So at x equal to 0, this f of x is equal to 0, and at x equal to d, because d square in the numerator cancels with d square in the denominator, this seems to be satisfying the boundary condition. Okay. Now if I try to find out what is d square f by dx square, right, which is what I should be able to find when if f of x happens to be another potential solution or another voltage, then differentiate this one twice. What do you get? Twice differential of x square is equal to 2. Okay. Is this quantity equal to 0? No, this quantity is not equal to 0. So in this case, you had a situation where the true solution, so if this is x equal to 0 and this is x equal to d, the potential at x equal to d happens to be V0, the potential at x equal to 0 is 0. The solution in between has to have a linearly varying, because you see that this is the true solution, right. So this is V0 by d into x. The slope of this line is V0 by d, and when you go a distance of d, you actually reach the potential of V naught. The potential that we had here was a quadratic one, that is assumed f of x is a quadratic one, which also starts at 0 here and ends up at V0, but it does so in a quadratic manner. Unfortunately, this potential does not satisfy Laplace, okay, and hence cannot be a solution. In fact, the solution that you obtain, if it satisfies Laplace's equation, if it satisfies boundary condition, that solution will always be unique. Okay. This is a very important thing to note. The second question is, can I always find the solution? Can I always solve Laplace's equation and then actually obtain a solution? I have already seen that if I obtain a solution subject to boundary conditions of the problem and the fact that that solution satisfies Laplace's equation, that solution will be unique. But will I always be able to find a solution? Turns out that except for pathological cases which we do not consider, there is a nice theory which tells you that these Laplace equations usually have a solution. Okay. So we do not really bother with the existence problem at this stage, we are only concerned with uniqueness, and we have not proved this uniqueness in a very rigorous manner, but we have given you the hint as to what can happen. So you might have a situation that once you obtain a solution, if that solution satisfies boundary condition and if the solution satisfies Laplace's equation everywhere, then that solution is unique. No other method can give you a different solution, right, because if the other solutions exist, then either they must be some linear multiple of the existing solution which anyway you have taken care of, or if other solutions exist, then either they do not satisfy Laplace's equation but satisfy boundary conditions, or satisfy Laplace's equation but do not satisfy boundary conditions, right. So in that manner you can actually see that there is only one unique solution for Laplace's equation, and that is what we are trying to find. Alright, now we have found the potential. Is it possible for me to find out the electric field? Why yes, electric field is given by minus gradient of V, and in this case V is a function only of x, so this becomes minus x hat del by del x, or rather d by dx in this case, since V is a function only of x, of V0 by d into x. And what is this? Differentiating this fellow, what you get is minus x hat, okay, V0 by d. Turns out that the potential, is actually negatively directed, which means that it is directed from the top plate. That makes sense because top plate is the one that was kept at a higher potential V0, and from the top plate the electric field happens to have a constant value of the electric field, okay. So this minus sign is telling you that the assumed x direction was from bottom to top. So this was my x axis, right, and this was my y axis. The electric field is directed from top to bottom, therefore there is a lines coming from the top conductor to the bottom conductor out there, okay, and the magnitude of this is given by V0 by d. So we see here that the electric field is coming from the top conductor to the bottom conductor, and it has a value of V0 by d, so it is a constant conductor. Now how do I obtain the capacitance? Well, to obtain the capacitance I need to know what is the total charge stored either on the top conductor or the bottom conductor. Now I know from boundary condition that if I consider a small region here, right, which might be the region that I consider over here, then in this region which just extends below, and I know that there is nothing in the below out there. So if this small region which has an area of say delta A, right, the corresponding charge enclosed must be equal to rho s into delta A, rho s being the surface charge density. But boundary condition for D tells me that if I have this is the electric field, the corresponding D field will also be like this, right. So the D field happens to be normal to this top conductor, and the normal D field, because there is no second D field, so there is only one normal D field, that must be equal to rho s, okay, and dn1 is nothing but epsilon times en1, that is equal to rho s, okay. So I can substitute for rho s as delta A epsilon en1, but what is the electric field? The normal electric field we have already obtained, and that is given by V0 by d, okay. So this is the charge that I have. Now this divided by the potential to which we have applied the potential difference between the two plates is actually given by V0, and this ratio will give you the capacitance C. There is a slightly more rigorous way of solving this one. I am skipping that one in the interest that I can get to another interesting problem. So this is the basic idea which is still okay. So you see that the potential difference is V0 that we have already specified. The total charge is given by delta A over this small patch delta A epsilon V0 by d. Clearly V0 cancels on both sides, and what I obtain is delta A epsilon by d, okay. Instead of considering this small patch of area, I can consider the entire area itself. So when I take the entire area, I am trying to sum up many delta A's such that they will all sum to one single A, and then I get epsilon A by d or A epsilon by d. So I usually remember this in the form of epsilon A by d, and this happens to be the capacitance of a parallel plate capacitor. So you might have actually used these relationships in your earlier studies without really seeing where this relationship is coming from. The moment you have kept two conductors at two different potentials or a potential difference between them, there will be electric fields generated, because there will be a different potential, there will be electric field, and this electric field is usually directed from the higher potential to the lower potential. And this electric field, if it leaves a particular conductor, it will always leave at a normal case. So as long as this is uniform, it will leave at a normal case. If it is not, then it will bulge and show all the fringing effects, which we will not deal right now. So our goal, after looking at this parallel plate capacitor, which might have seemed to be too excessive, is to consider another interesting example of a transmission line. Remember, parallel plates can also be used as a transmission line, or their cousins parallel wires can be used as transmission lines. Now we are considering another transmission line which we call as a coaxial transmission line. So, we have already discussed this coaxial transmission line. In the coaxial line, what you have is an inner conductor of diameter 2a and an outer conductor of diameter 2b. Usually you connect the outer conductor to ground and then the inner conductor you connect it to a voltage source. Okay, so you connect a certain voltage source to this one, so that inner conductor is usually at a higher potential and a constant potential. We will again consider that the inner conductor is at a potential of V0. Okay, but then we have a small problem here. Well, the structure is actually a cylindrical system, right? It has a cross section which is circular, but then it also has an axis along z axis. Okay, as long as we consider a uniform cross section and the cross section appears to be something like this. Okay, the inner circle has a diameter of 2a, the outer circle has a diameter of 2b as we have discussed. Okay, so in this case, and I have also kept the inner conductor to be at a higher potential which is at V0, and I have considered the outer conductor to be at a potential 0 volt. Okay, so if this cross section is maintained as you keep going along the z axis, then it is possible for us to obtain electric field and calculate the capacitance of this structure, okay, without actually solving Laplace's equation in the 3 dimensions. So, we are going to solve Laplace's equation in the 2 dimensions. So, you have del square V equal to 0, and now we need to first specify the boundary conditions as well. Well, we have already specified the boundary conditions by keeping the inner conductor at V0. Thus, at R equal to A, right, this is the first boundary condition. The potential at A will be equal to V0, and the second boundary condition is that at R equal to B, where R is the radial distance, okay, the potential V at R equal to B will actually be equal to 0. Okay. Now, V can depend on R, phi and Z in general, since we are considering only 2-dimensional Laplace's equation. So, we have no Z dependence, but now can our potential depend on phi? Again, do the test. Suppose this is my coaxial cable. Okay. Now, if I keep moving around this coaxial cable, does this cable look any different? Right. So, imagine this and then keep moving around like this. Does this look any different? In this case, the pen looks different because there is some mark out there, but if you just imagine this surface and you keep moving around, there is absolutely no difference. So, the potential does not have a phi component, that is, as you move around there is no difference out there. However, if you keep moving away from this one, right, and you reach the potential, you reach the circle at R equal to B, then the potential has to drop to 0 there. So, potential must start here at V0, and as you move away from it and reach the second conductor, you must have to, it has to drop to 0 there. So, this potential is actually function of only R. Okay. So, lucky for us, our problems are not so difficult. We have the potential only as a function of R. The only small difficulty is that we need to know what is this del square V equal to 0 in the cylindrical coordinate system, and I won't bore you with the details of derivation of that one, but I will just give you quickly what is the corresponding expression. Since V is function only of R, I can replace the partial derivatives with the full derivatives. So, I have 1 by R d by dr, R dV by dr, this being the del square V component for which this particular problem is concerned. So, for this problem, del square V equal to 0 actually reduces to this equation. We are of course not considering the case when R equal to 0, our boundary starts at A and then ends at B. Therefore, this equation equal to 0 also implies that R dV by dr must be some constant k, and therefore dV by dr is equal to constant k by R, which allows me to integrate once more and then say V of R is equal to k log R plus d. So, this is the general expression that I have. I need to apply the boundary conditions and then find out the actual values of k and d. So, I will do that one by first considering the boundary condition at B, because I know V of B, the potential at that R equal to B will be equal to 0, and this is equal to k log of B plus d, and d of course solving this one gives you minus k log B. Then V at A is equal to V0, that is the inner conductor is kept at a potential V0. So, this is V of A equal to V0, okay, and this one once you put in you can then solve for k happens to be V0 by log of A by B. I will just leave this as a small exercise to you to show that this is indeed the correct solution. and therefore V of R anywhere between the regions of inner and outer conductor, this V of R is given by V0 by log of B by A, B is larger than A, times log of B by R. Okay. So, this potential, does it satisfy Laplace's equation? I hope you can show that it actually satisfies Laplace's equation. And what happens when R is equal to B? The potential drops down to 0 because this would be log of 1, so it is gone. What happens when R equal to A? This would be log of B by A in the numerator divided by log, which is a natural log I am talking about, log of B by A, so that will actually be equal to V0. So, this is the unique solution for V. How about electric field E? E is minus gradient of V. Again you need to find out what is the expression for the gradient in cylindrical coordinate system, and then you can show that this is simply equal to minus r hat dV by dr. I just obtained this one from the math handbook, and then if you put in this equation and then solve it, you obtain the electric field as radially directed R0 V0 divided by R log B by A. So, there is some constant out there, but then the electric field is actually along radial, but as you keep going away the electric field is actually dropping down. Okay. And the potential of course starts off with V0 at R equal to A, and then in logarithmic way goes down to 0. So, the constant potential, so this is at R equal to A, the potential is V0, the potential actually goes as a log all the way up to 0. So, you will have constant potentials. Okay. So, these are the constant potential contours, and then the electric field will be perpendicular to this, and the electric field in this case will also be going down in terms of the radial direction, and it will be going as 1 by r. It will not be a constant electric field out there, and this is the electric field that you are going to obtain. Now that you have obtained the electric fields, then what you need to do is to kind of find out what is the overall charge. So, I know D is related to electric field in terms of epsilon times E. So, D will be given by r hat epsilon V0 divided by r log B by A. Now, what I am interested is to actually find out what is the charge on the inner conductor. Again I have to emphasize that I am not going to consider the z axis. Okay. So, or I will consider inner conductor means I am actually going to consider a very small amount of delta z. Okay. And then put a surface around it. So, this is the inner conductor over which I am trying to find out. So, once I find out what is the charge here, then I take that charge, divide by delta z, so as to take away all the z dependence. Okay. So, you can show that this is nothing but integration over delta z 0 to 2 pi, right, because this one is happening at r equal to A, you have to evaluate D at A, okay, and ds is given by r or A d phi, right. So, this A d phi along r direction and delta z. So, I am going to integrate this one over delta z as I told you, and you evaluate D at A. So, r equal to A will be the condition. So, you have epsilon V0 by A log of B by A, right, and then charge divided by delta z is what I will call as the line charge density rho L, and this line charge density rho L will be equal to, after you integrate this equation, and since this integral over d phi will simply pull out a 2 pi to you, 2 pi at the outside of the integral. So, you get epsilon V0 2 pi, A will cancel in the numerator and denominator, you get log of B by A. Okay. Now, what is the applied potential? The applied potential difference between the two conductors is V0. So, now if you define what is called as the capacitance per unit length, you get rho L divided by V0, which is a line charge density on the inner conductor. I am only considering the inner conductor, you can do the problem by considering the outer conductor. It is slightly more difficult to apply Gauss's law to the outer conductor, therefore, we did not consider that. But over the inner conductor you have to consider a closed surface, and this surface has to have a small length delta z along with it. Okay. Then you divide all the quantities with respect to delta z in order to take away the z dependence. So, now you have a capacitance per unit length rho L by V0, which is given by 2 pi epsilon divided by log of B by A. This is a very important relationship for a coaxial cable. You should remember this quantity or this particular expression. Now, you might ask, how about the inductance per unit length? I mean, why am I interested in inductance per unit length? Because I know that for a coaxial cable the characteristic impedance Z0 can be given by inductance per length divided by capacitance per length, and there are ways of actually measuring what is Z naught. Okay. So since I know how to obtain Z naught, I can first square this, so I get Z0 square equal to L PUL by C PUL, and I know how to measure this left hand quantity Z naught square. I know how to calculate this capacitance. Calculating inductance in this case is simple, but it is not really necessary. So if you know what is the Z naught of a coaxial cable, you know what is the capacitance per unit length of a coaxial cable calculated from this expression, you can easily substitute for CPUL and then write down or find out what is LPUL, which is the inductance per unit length, and this is given by 1 by Z0 square CPUL. So this completes our couple of solutions for Laplace's equation. Now you might have lot of questions over here. So what we have covered is just barely scratching the surface. We will consider the two-dimensional Laplace's equation and solving the two-dimensional Laplace's equation in the next module. But here is one very important question. We talked of parallel plate capacitors, we talked of parallel wires. We didn't calculate we didn't solve Laplace's equation for parallel wires, but you can do that one as well. And then we calculated capacitance of a very important transmission line called as coaxial transmission line. However, you must have noticed something. Coaxial lines, wires, plates are all supposed to be used at very high frequencies, which means that the potentials that you are applying are not going to be constant potentials, right? So they will be changing with respect to time. So in those cases, whatever the capacitances that we have calculated, is these formulas valid? The formula that we have calculated comes from an electrostatic point of view, where the fields are not varying with respect to time. So strictly speaking, these formulas and the electric field that we have obtained are all valid only at DC frequency, that is only at DC, not when the frequency is different. For low frequencies, one can neglect the changes in the electric field and consider pretty much to be constant, but to be really true, these equations have to have what is called as correction terms, and these correction terms can be calculated using Maxwell's equations, or you can use what is called as quasi-static analysis and then calculate the correction terms and keep adding these correction terms until your solution essentially converges. And this quasi-static analysis is a subject of some other module in this particular course. So in the next module we will talk of two-dimensional Laplace's equation and then solve one Poisson's equation to round up our study of electrostatics. Until then, thank you very much.